Hello everyone, welcome to my lecture on Thermoelectricity Session 56. Teaching points. Thermoelectric diagram or tide diagram, determination of A and B, that is Seebeck coefficients, types of thermoelectricity, to determine the neutral temperature, to determine Peltier coefficient, and to determine Thomson coefficient, and also to determine the thermo EMF of a thermocouple. These are all uses of tide diagram. Learning objectives. To know about the concept of tide diagram and determination of A and B, that is Seebeck coefficient, and to analyze the type of thermoelectricity and how to determine the neutral temperature by using tide diagram, and also to determine Peltier coefficients, to determine Thomson coefficients. Prerequisites. Student must know the meaning of thermoelectricity, Seebeck effect, Peltier effect, Seebeck coefficient, meaning of thermocouple, Peltier coefficient, neutral temperature. Thermoelectric diagram or tide diagram. A diagram showing the relation between the thermoelectric power dE by dt or dE by d theta and the temperature of hot junction with cold junction maintained at fixed temperature is called thermoelectric diagram. Uses. Tide diagram can be used to determine the Seebeck coefficients A and B. Thermoelectric EMF is given by A theta plus B theta square. Thermoelectric power is dE by d theta, that is P equals to A plus 2B theta. A graph of P, that is dE by d theta versus theta, is a straight line. The slope of this gives the positive, or slope gives the value of 2b, and the intercept gives the value of Seebeck coefficient A. Thermoelectricity. From thermoelectric diagram, we can also determine which type of thermoelectricity. If the slope of the line is positive, then the Thomson coefficient is positive, then the effect is positive Thomson effect. For a metals like iron, the slope is negative, hence the metal has negative Thomson effect. Hence, from the power line indicates the type of thermoelectricity. To determine the neutral temperature. The point of intersection of thermoelectric power lines correspond to theta n. Here, it gives the point of intersection of thermoelectric power line corresponds to theta n and gives neutral temperature, that is theta n. So this is a type of thermoelectricity, positive Thomson effect and negative Thomson effect. The slope of this copper is power line is positive, then this is positive Thomson effect. This is the slope is negative for the metal iron, and this shows the negative Thomson effect. The intercept, this is A, and here this is tan theta, the theta. And tide diagram is also used to determine the Peltier coefficient. Here Peltier coefficient for a metal B with respect to A at the temperature T1 is OE1 into OP1. So that is pi1 equals to area of OT1 into OP1. Thermoelectric power between A and B at temperature T1 is equals to PQ, and the Peltier coefficient between A and B at T1 is equals to OT1 into PQ. Then pi 2 equals to area of rectangle, that is P1P Q1. So it is shown in the figure. So here OT1 P1. This is the Peltier coefficient for a metal B with respect to a metal A, and this area that is OT1P1. So area of OT1P1 gives pi 1. Then this the thermoelectric power between A and B is PQ. Peltier coefficient between A and B at temperature T1 is equals to the area of rectangle P1 Q1. And the type diagram is also used to find the thermo EMF of a thermocouple. Here considering the two thermocouple formed with the two metals A and B, let T1 and T2 be the temperatures of the two junctions. Here the thermo EMF is equals to net energy absorbed is equals to area of PQLN. So this area gives the thermo EMF of a thermocouple. And the type diagram is also used to determine the Thomson coefficient. The Thomson coefficient of a metal B at the temperature T1 is equals to T into d square E by dt square. From graph, T equals to T1 plus T2 by 2. This is the average of these two temperatures T1 and T2. Then d square E by dt square is equals to QL by PQ. So that is equals to QL PQ. So see here PQ is nothing but T2 minus T1. Hence sigma B Thomson coefficient is equals to T into QL by T2 minus T1. Thomson coefficient in B between T1 and T2, it's given by T1 plus T2 by 2 into QL. That is nothing but sigma equals to area of trapezium. Area of trapezium P1 L1 L. So this is the area of trapezium. So we know how to find out the area of trapezium, that is half into height into sum of parallel sides. So this is the parallel sides and this is the height. So that gives the Thomson coefficient sigma. So that is area of trapezium, that is P1 L1 L. Session summary. Understanding the applications of thermoelectric effect, understanding the meaning of tie diagrams, understanding the uses of thermoelectric diagram. Thank you.